You build an app that runs perfectly in testing, but the moment it hits production and faces a massive influx of data, the system chokes. This failure often traces back to a nearly universal developer habit, defaulting to the array for every data collection. Arrays handle small lists effortlessly, but as those lists grow into the millions, they reveal a hidden structural flaw that kills performance. This occurs because of linear time, the mathematical reason why some data structures cannot handle high-volume traffic. When scale increases, it exposes the inherent inefficiency of these linear structures in modern high-speed applications. To understand the lag, we need to look at how an array executes a basic search command, like .contains. An array is forced to search sequentially. It starts at the first box and checks every single item, moving from top to bottom. In a worst-case scenario, where your item is at the very end, the system must scan every preceding element before confirming the match. This is O of n, a state where the time required for a search grows in direct equal proportion to the amount of data you store. Relying on O of n searches for large-scale tasks builds a computational delay into the core of your software. To eliminate that delay, we shift our focus to the immediate algorithmic alternative, the set. While an array is bound by linear time, a set operates on constant time, or O of 1. This efficiency comes from the hash key mechanism. Instead of scanning the cloud of data, the system uses a key to jump directly to the target's location. This takes the same fraction of a second whether the collection contains 10 items or 10 million items. You are replacing the slow top-to-bottom scan of an array with an instant, direct retrieval. Removal to a set replaces the exhaustion of a manual data scan with the efficiency of direct addressing. Gaining this speed requires your data to meet a three-part structural checklist. First is strict uniqueness. Sets only store an item once. Any duplicates you attempt to add are automatically blocked by the system. Second is order and sensitivity. Because sets are completely unordered, the sequence of your elements cannot matter to your app logic. Finally, your data types must conform to the hashable protocol. Standard types like strings and integers handle this by default, and custom models can be configured to allow the system to index them. Achieving this O of 1 speed requires a trade-off. You give up chronological order and repetition to gain high-speed, hash-driven precision. Applying this in a real-world coding environment is a matter of auditing your logic. Look for areas where your app is slowing down, and determine if you're using order-dependent arrays where order isn't actually required. In many cases, the fix is as simple as changing the word array to set in your code. When explaining your choices to an interviewer, emphasize that this switch turns a slow O of n search bottleneck into an instant O of 1 operation. Engineering mastery is found in selecting the precise data structure that fits the specific constraints of the problem.